Forget everything you think you know about the world. Quantum physics came to completely transform our view of reality, creating a whole new set of fundamental rules. It's not just a bunch of crazy equations. It's what makes your phone work, what enables advanced medical exams, and what might one day explain how the universe really began, and perhaps how it will end. But hold on, you don't need to be a genius to understand this. Today, you're going to discover why discrete energy changed the history of science, how photons control light, why particles emerge from nowhere, and what all of this reveals about the very nature of reality itself. Get ready, because every minute of this video, one of your certainties might disappear, and in its place emerges a new way of seeing the world. At the beginning of the 20th century, science stumbled. The old laws could no longer cope. Something unusual was happening, something that classical physics couldn't explain. That's when quantum mechanics was born, a new way of looking at the world and questioning everything. But hold on, this didn't stay just in books. When you turn on your phone, use a computer, or get an MRI, you're using quantum physics without knowing it. Even positron emission tomography, used to diagnose tumors, depends on antiparticles predicted by these revolutionary ideas. That's right. Things that seemed like fiction, today, save lives. And it all started with uncomfortable questions. Why does light behave that way? Why don't certain reactions obey the rules? The answer was a slap in the face to classical logic. And from then on, nothing was ever the same. Want to understand why? Then take a deep breath. Because in the next point comes the first real break with the old world of science. For centuries, the idea was simple. The universe worked like a clock. Each gear moved with precision, and everything could be predicted. It was the so-called determinism. But then came quantum mechanics, and threw that security out the window. It showed that reality, deep down, is made of probabilities, not certainties. The breakthrough began with a disconcerting concept: discrete energy. Contrary to what was thought, certain phenomena don't happen continuously, but in packets, the famous quanta. This destroyed the notion that physical processes follow a smooth and uninterrupted line. Instead, the world began to function in invisible, but fundamental jumps. This paradigm shift was like changing the manual of reality in the middle of the game. Quantum mechanics not only changed the way we understand matter, it revolutionized the very idea of what is real. Because if everything depends on probabilities, and nothing can be predicted with absolute certainty, what, after all, is the truth? This question echoes to this day, and the answer begins with a dilemma that kept physicists awake at night: the black body problem. At the end of the 19th century, scientists faced an enigma that seemed trivial, but hid a conceptual bomb. When studying the radiation emitted by a black body, they noticed something peculiar. Classical equations simply failed. Worse, they predicted that an object should emit infinite energy. This became known as the ultraviolet catastrophe. And nobody could solve it, until Max Planck appeared. With a bold and somewhat desperate proposal, Planck suggested that energy wasn't continuous. It was emitted in discrete packets, called quanta. That's how the idea of discrete energy was born. He solved the problem. But without realizing it, he had opened the door to a whole new physics. The most curious thing? Planck didn't even like his own theory. He thought it was just a temporary mathematical trick. But that trick would change everything. It was the beginning of quantum mechanics. And soon, another genius would take an even more radical step, proving that it wasn't just matter that came in packets. Light itself did too. And that's when photons entered the scene. Shortly after Planck's proposal, Albert Einstein entered history and caused even more commotion. He analyzed an intriguing phenomenon: the photoelectric effect. When light hits certain metals, it knocks electrons out of them. But the strangest thing? Not all light did this. And increasing the intensity didn't always help. How so? Einstein had a bold idea. What if light was also made of packets? Not continuous waves, but energy particles, the so-called photons. Each photon would carry a specific amount of energy, and only those that had enough energy could remove an electron from the metal. This explained the effect perfectly, and consolidated the idea that nature is quantized. This insight was so important that it earned Einstein the Nobel Prize. But more than that, it placed light and everything that involves it on a new level of understanding. What once seemed like a smooth and constant wave now revealed itself as a flow of units, packets, quanta. The universe was showing itself to be much more fragmented and fascinating than anyone could imagine. This discovery about the dual nature of light paved the way for understanding other fundamental aspects of matter. And this logic of jumps would soon appear within the atom itself, revealing even deeper secrets about how reality works at its most basic scale. You've probably heard that electrons stay around the nucleus of an atom, right? But what almost nobody tells you is that they can't do this in just any way. Niels Bohr discovered that these electrons can only occupy specific energy levels, as if they were well-defined floors of an invisible building. In other words, there's no middle ground. Either the electron has enough energy to be at that level, or it doesn't. And there's more. To change energy levels, the electron needs to gain or lose an exact amount of energy. This helps explain why each chemical element emits light in a different way, as if each one had its own exclusive color in the universe. This light pattern is called emission and absorption spectrum, and became a kind of fingerprint of atoms. Now think about this. This is happening inside you, right now. Trillions of electrons changing energy levels, emitting and absorbing energy in absolute silence. Your entire body functioning based on these invisible and totally quantized jumps. It's as if you were made of small, well-choreographed secrets. And the deeper we look, the stranger everything gets. When scientists thought they had already understood the basics of particles, came another surprise: spin. Contrary to what the name suggests, it's not exactly a rotation like that of a spinning top. It's an intrinsic property of particles that has no direct parallel in the classical world. It's as if each particle had an internal sense of rotation that only makes sense within quantum mechanics. The most fascinating thing is that this property makes the electron behave as if it were a tiny magnet. This helps explain why certain materials, like iron, can be magnetized. But spin isn't just for that. It's also essential for understanding the structure of atoms and even for making modern technologies work, like magnetic resonance imaging. It seems small, but it's huge. Spin shows that the quantum world has its own rules. No simple analogies with everyday life. In this universe, particles have properties that defy our common sense. And when you put it all together, quantized energy levels, photons, discrete energy, and now spin, the result is a world much more complex than classical physics ever imagined. And even more surprising is what comes next: an equation that predicts all of this based on probabilities. Classical physics love to predict everything with precision. You could calculate the trajectory of a planet or the fall of an apple with almost frightening accuracy. But in the quantum world, none of that works. Here, probabilistic nature reigns. And who gave shape to this was Schrödinger's equation, a formula that doesn't say what will happen, but what are the chances of it happening. It seems strange, but it works. Instead of stating the electron is here, quantum mechanics says it has a 70% chance of being here and 30% of being there. This radical change took determinism off the throne and put probability at the center of predictions. And the most incredible thing? Even without guaranteeing certainties, the results are incredibly precise. This approach generated suspicion at first. Einstein himself didn't easily accept the idea. He said that God does not play dice with the universe. But time proved otherwise. Quantum mechanics began to predict phenomena with impressive accuracy. From lasers to computer chips, everything depends on these equations that speak in the language of chances, not certainties. And if this already seems challenging, wait until you meet what comes next: the uncertainty principle. Now hold on to this. Even with all the equations and predictions, there's a natural limit to what we can know about a particle. It's called the uncertainty principle, formulated by Werner Heisenberg. For an even deeper dive into this concept that turned common sense upside down, check out our video, Why Nothing is in Its Place. But stay here because I'll link this video in the card at the end. In summary, he showed that it's impossible to know, at the same time, the exact position and the exact velocity of a particle. The more you try to measure one, the more you lose track of the other. It's not an instrument error. It's not lack of technology. It's a fundamental characteristic of nature. This principle finally topples the idea of absolute control. In the quantum world, precision has a price, and this even messes with our notion of reality. After all, if you can't even say for sure where a particle is, how can you trust that reality is something fixed? This concept became one of the greatest symbols of quantum mechanics, and also a challenge for those who still wanted to believe in a 100% predictable universe. It was the final blow to classical determinism. From here on, the subatomic world revealed itself to be more surprising, more unstable, and ironically, more fascinating. And what seemed like theoretical madness soon began to take real form, with the discovery of particles that no one had ever seen. When scientists united the ideas of quantum mechanics with relativity, a bold prediction emerged. There should exist a particle identical to the electron, but with positive electric charge. And the most incredible thing? This particle was actually found later. It's called the positron, and it was the first antiparticle ever discovered. It works like this. For each known particle, like electron, proton, or neutron, there exists a twin sister of the opposite, with opposite charge. When a particle meets its antiparticle, the two cancel each other out and release pure energy. This phenomenon, which seems like science fiction, really happens in the universe. And even in hospitals. The technology called positron emission tomography, PET scan, uses precisely this process to identify diseases. In other words, a theoretical idea became a medical tool. This showed how powerful quantum physics predictions are. And as these theories evolved, an even more ambitious proposal emerged to unify the forces of nature into a single structure. And that's where the so-called Higgs boson comes in. Quantum physics didn't stop at atoms. It went even deeper. Then emerged quantum field theory, a way of understanding the universe as a set of invisible fields that fill everything. Each particle we know would actually be a little wave in these fields. Sounds strange? It is, but it works. With this theory, scientists managed to put together several pieces of the puzzle. That's how the standard model of particles was born, which explains 3 of the 4 fundamental forces of nature: electromagnetism, weak force, and strong force. This model predicts how particles interact, what keeps atoms stable, and even how the sun produces energy. But one piece was still missing. Why do particles have mass? The answer came with the famous, and for a long time invisible, Higgs boson. It would be the particle responsible for giving mass to all the others. For decades, it was just an idea. But in 2012, it was finally detected. And with that, quantum physics proved once again that its revolutionary ideas were right all along. Quantum physics invites us to do something rare. Accept that we don't know everything. That the universe is more mysterious, fragmented, and unstable than we imagined. But also more fascinating. Because within each photon, each spin, each probability, there exists a clue, a chance to better understand reality and, why not, ourselves. And now that you've already taken this dive into the ideas of Max Planck, Bohr, Einstein, and so many others, the question that remains is, what are you going to do with this knowledge? Are you going to face the world the same way? Or are you going to look at everything, even the invisible, with more curiosity? If this video messed with your ideas, don't forget to subscribe to the channel and activate notifications. Because here, with each new episode, we go deeper into the unknown. Because knowledge is just the beginning.